Let's continue our discussion about dynamic watermarking. So if you recall, the idea in dynamic watermarking was that you will add a small noise to the control signal, and that will create a dependence between the observation and the action, and that will allow you to detect the attack. So the picture I want you to have in mind: you have actuator, you have plant, you have sensor, this is channel with an attacker, here we have detector and controller. Excuse me. And this is the overall structure. This is XT, or maybe this is no, let me just keep it XT. This is YT. Excuse me. This is UT. I hate having cold. So bad. Plus, what was the random signal we added? ET? What was the random signal? Beta T, ET?
It's like a scribble. I don't know what it's called.
Okay. Show me what symbol it is. Oh, okay, it's CT. CT, and that goes into the actuator. So this this is an independent noise. And this CT forces correlation between XT and CT. This forces correlation between XT and CT, and if you don't find that correlation in YT, then you declare that there is an attack. If you find that correlation in YT, then you say that there is no attack. Now the problem in today's class is, we know how to do this. This is, by the way, your assignment 5. You have to do this in assignment 5. I know some of you have already completed assignment 5. Some of you might still be working on it. So that's the way to detect the attack. In the case of a general system where this, so remember here the control action is such that you can add two numbers in order to get the control action. So if you're supposed to let's say increase the temperature by 5 degrees Celsius, and then you add a small noise of 0.5 degrees Celsius, then you can add the two numbers, and that's what your control action is going to be. Now consider a situation where your control action is on or off. You can either turn something on or you can turn something off. Your state is just 1, 2, 3, 4, 5. Okay, you no longer have a Gaussian random variable. You can no longer add something to the action. In on and off, what do you mean by adding something to the on signal? Either it's on or it's off. There is no other intermediate signal. So how would you force this correlation between CT and XT? This is the correlation that we want to force between what's coming out of the sensor and a private signal that I'm introducing in the control action. How would you force the correlation in the case of on-off situation, or where X is just on-off or open-close or some categorical variable? Categorical variable means it has categories. It's red, blue, green, okay, or it's on and off, or it's open or close. And same thing with UT. UT could be also categorical variable, which is it's on or off, it's open or close, or it's red, blue, or green. How would you add two actions in that case? You have a red light, blue light, and a green light. What does it mean to add red light plus green light? Any thoughts? You want to introduce a private signal within the control action. How would you add that private signal in a categorical situation? So XT, X, categorical, and U, categorical. So the state space and action space, both of them are categorical. So you can think of just state space as 1 to n and U as 1 to m. So we thought about it back in 2020, maybe 2019, 2020. My research group was working on this with Ford Motor Company. And so we came up with the following idea. Remember that the policy gamma t or gamma maps state to action in the general, in usual cases. We said that, okay, let's try to do something more complicated. Let's define the policy gamma from X to probability distributions over U. Now I can add stuff, okay? Once things are in the probability space, I know how to add two probabilities. I know how to add a probability measure with another probability measure. We'll get to it in a bit, okay? So this is P of U is basically vector P in 0, 1 raised to m. Remember, U is m dimensional, such that summation of Pi is equal to 1, I equals 1 to m. This is the set of probability distributions over U. Okay, so this was our thought process at that point of time. So instead of looking at deterministic policies which maps a specific state to a specific action, we will look at randomized policy So in the randomized policy, we map state to probability distributions over action. Now what happens if you have a deterministic policy? How do you convert a deterministic policy into a randomized policy? Well, what you do is the action that you wanted to take under the deterministic policy, it gets probability 1. All the other actions would get probability 0. That's the way to extend a deterministic policy into a randomized policy. So this vector P, so if gamma x was deterministic, in this particular case, gamma x will be 0, 1, 0, 0, 0 kind of vector. Okay, so that's how you make it a randomized. You convert a deterministic policy into a randomized policy. Now, what do I mean by adding a small independent noise to my action in this particular case? Once you start caring about randomized policy, how would you add a small noise to your action space, to your action? Any idea?
You can add a vector and make sure that the constraint is satisfied.
You can add a vector of another probability measure,
And then make sure
and hopefully that, yeah, you will add it in a way that this particular vector constraint is satisfied. Awesome. So what we will do is, we have gamma star, which is the original policy. The watermark policy is going to look as follows. One minus beta gamma star plus beta nu, and this is the watermark. Beta is a variable 0.02, something like 0.02. Okay, so I start with an original policy. So somebody told me, like my supervisor, the department chair told me that the policy is, if x is the state, then u is the action. I convert it into a randomized policy. So if x is the state, 0, 1, 0, 0 is my action. Okay, so that's my randomized policy. So I converted the policy that was given to me into a randomized policy. That's my original policy. Now I want to watermark it. So what I'll do is take a convex combination of my original policy with a watermark policy. So watermark policy is like a small policy. So nu of x would be something where each of this entry is greater than 0. Like, it's not required that it be greater than 0, but it's beneficial if all the entries are greater than 0. It will improve your detection performance quite significantly. So I pick a watermark policy. I can pick it any way I want to, as long as many of the terms are going to be non-negative or positive in this particular vector for all possible values of x. That becomes my watermark policy. I take the convex combination, but look at the multiplier here. So beta is close to 0.02. You can make it 0.01, you can make it 0.05, depending on what the strength of the watermark you want. So this is the watermark policy, this is the strength of the watermark. So if beta equals to 1, then your watermark policy is completely a watermark, like there is no control signal here. And if beta is close to 0, then it's a watermark policy where majority of the time you are implementing gamma star, and sometimes you are implementing this policy nu. Now the question is, for this particular case, you use chi-square detector or you use many of the other detectors in order to compute, in order to figure out whether the attacker has attacked this particular channel or not. Now the question is, how do we do the same thing in this particular case? Now the problem is that whatever detector we talked about here, required Gaussian assumption, like it required all of these variables to be vectors, and it required the assumption that the noises and everything is Gaussian and well defined. Now the problem is, if you have this discrete state setting, you can't really have a Gaussian distribution. We can't even talk about Gaussian distribution. So we need to figure out a way to detect the attack on this kind of system where you have categorical state. So let's talk a little bit about that. Can I erase this side? Actually, I'll erase both the sides. Yeah, I guess I'll erase it. Oh, I need to talk about the attack model. So the attack model we consider is that the attacker is going to pick a function phi which maps x cross x to a distribution over x. So the attacker picks yt that is distributed according to this quantity. Okay, so under no attack, detector observes. Can someone tell me what all things detector knows at the time under no attack? Detector observes x1, xt, at, ut. T equals, I might use S here. Am I using S or what am I using? I guess S is fine. Have we used S until now? I don't think so, right? Let me just keep it S. So detector has observed XS US all the way from S equals to 1 to current time t by the time t under no attack. What does the detector observe under attack? What does the detector observe under attack? What data is going to the detector? Remember that the adversary is changing the information, the state information that is going to the detector, going to the controller. So actually detector observes ys us s equals to tau to t at time t where tau is basically when the attack started. So before the attack, the detector is observing the current state and the current action. After the attack, the detector is observing the attacked state and the actions that the detector has or the controller has implemented. Remember that the detector and the controller are sitting at the same location, so they can share observations with each other. So what is the problem here? What do you think is a hypothesis test here? How do you set up the hypothesis test in this case for attack detection? What is my null hypothesis? H naught? Oh, we did not talk about the transition probability. So let's talk about the transition probability. So this is probability of xt plus 1 equals to j given xt equals to I and ut equals to this is I prime j. I'm going to denote it by R I J I prime. So it's a three-dimensional matrix, okay? It has three indices, I, J. I stands for the current state, J stands for the current action, I prime stands for the next state. And this transition probability is known because I know the system model. So this is equivalent to knowing the system model. It's equivalent to knowing the ABC matrices that we used in the previous lecture. Okay. So I know the transition probability because I know the system model. I know exactly if the current state is I and the current action is J, what's the probability that I'm going to see I prime at the next time step. That part is known. If I'm applying the control policy gamma, then gamma is basically, you can view it as a matrix Ij, which is the probability that ut equals to j given xt equals to I, and then you can think of I prime, j is already used, L, probability yt plus 1 equals to L given xt equals to I, xt minus 1 equals to I prime, or I prime and I. So under no attack, the controller is making an action on the basis of xt In the case of attack, this xt will be replaced with yt, because that's the observation that the controller has. So in the case of no attack, the transition matrix, I don't think we need the transition matrix, so I'll just let it be. I think this is the only matrix we will know for the attack detection. But I'll tell you what's happening here. So I want to notice that there is a probability distribution yt plus 1, xt plus 1, ut plus 1 given yt, xt, ut. That's the overall transition kernel for the entire process. Oh, yt plus 1, xt plus 1 and xt. So make a correction here. This is xt plus 1 here, and this is xt equals to I. That's for this particular matrix. There is a small correction to be made. So by composing these matrices and doing the matrix multiplication in an appropriate fashion, you will get that this is the overall transition probability of the tuple yt, xt, ut. Okay, so you look at the overall process, the attacked observation, the true observation, and the action. And sometimes when the attacker is not present, this yt is exactly equal to xt, and this yt plus 1 will be exactly equal to xt plus 1. In the case of an attacker, these two numbers are going to differ. But the problem is detector only has observation. He doesn't, in the case of an attack, it doesn't know what xt is going to be. So that's the problem that we are trying to solve. So now the question is, what is the hypothesis test that we need to set up in order to detect an attack? So this is how we will set up the null hypothesis, which is there is no attack. So we will say that xs us s equals to 1 to t comes from the probability of Rij I prime. That would be the transition kernel for H naught. Actually, I should replace this xs with, anyways, under no attack, this is going to be xs. In the case of attack, this is going to be ys. Does not follow Rij I prime. If you think about it, this is exactly what we are doing in dynamic watermarking as well, except that the way we set up the hypothesis test there is that the residual satisfies certain conditions or the residual doesn't satisfy those conditions. But here there is no concept of residual because the states are categorical. The states could be red, blue, green. This I could be red, blue, green. This ut could be equal to on and off, and this could be red, blue, green. So there is no notion of residual. So the way we replace the residual here is to check for whether the transition kernel is coming from what we already know or it's some other random transition kernel. which is something that we do not know because we don't know what the adversary is going to use. We don't know what this phi is going to be. So this is the case with unknown post-change kernel. So I know the pre-change kernel, pre-change transition probability. So my pre-change model is known, my post-change model is not known. How would you set up the test statistics for this particular case? It's something that we have probably studied already. I think when I was teaching you about change detection in Markov kernels, we did talk about how do you do the detection when you don't know the when you know the pre-change kernel, but you don't know the post-change kernel or post-change transition probability matrix. How would you do it? What comes to your mind as a step one? So I have the entire history. I'm looking at the history. I have like the historical information of the state action pairs, and I want to check whether those state action pairs are generated according to this probability or this probability. What would you do? You see a bunch of data set, you want to know if it's coming from this probability or not coming from this probability. So here is the algorithm, something that we talked about. So we'll estimate from the data, we will estimate what this transition kernel is. If the estimated transition kernel is the same as the kernel I expected, then we are good. We are in good shape. On the other hand, if there is a lot of discrepancy between what we estimate as the transition kernel and what we expect, then we will raise an alarm. So we define two quantities. You don't have to note it down, I'll just write it, but it's I think this should go from B1 to B2. And then I have N B1 to B2. And then I define Q hat. So I figure out what's the number of times I have observed L, J, L prime pairs what's the number of times I have observed Lj pair, and I'm going to take the ratio. This is number of times. We had talked about it a few classes ago, how to compute the empirical probability distribution. So this is the number of times I have seen L, J, L prime pairs or tuples. And this is number of times L and J tuples or Lj pair was seen. And then we take the ratio. And this is my estimated transition kernel. And now I need to check whether this is close to this or not. How would you check that? So I want to check this is close to this. Remember that if yt was equal to xt, then this thing should be exactly equal to, well, not exactly because you are taking the samples, but this one should be close to this. How would you check?
Log likelihood.
Wonderful. That's what you are doing right now in the assignment. So what we will do is we'll look for summation of t equals b1 to, I don't want to write it here, but I need to set up the test statistics somewhere. How do I do that? This is my log likelihood function. There is a little bit of complexity here. So you want this to be greater than 0. You want this. So you want this to be greater than 0 when you are computing the log likelihood. So you need to put that constraint in the if loop right before you compute this log likelihood, and then you are evaluating it at this L, J, L prime tuples that you have observed in the past. Right? So that's how you compute the log likelihood. So you compute this. I'm going to give it a name S B1 to B2. And then my usual Q sum test statistics would be ZB2 equals to max S B1 to B2, B1 is less than equal to B2 minus capital M. and my rejection region is tau is already used. Where did we use tau? Oh, tau is when the attack started. Tau is already used now. So whatever, rejection region is something infinity. C, let me use C. So C infinity, that's my rejection region here. So I'll pick a number C, positive number C, and as soon as ZB2 goes above C, I'm going to raise an alarm that looks something is wrong. Otherwise, I'm not going to raise any alarm. The thing we proved in the paper is that this algorithm will always detect if there is an attack, if there is a persistent attack, it will detect the attack with some constraints on the mean time between false alarms. So it's not like we will not have false alarm, but certainly we will have attack detection. That's what we wrote in the paper, and we submitted it to I think couple of years ago when we wrote the paper and submitted it, and it's still under the review process. So I don't know if you're aware, but in our area the review goes on for 2 years, 3 years, 4 years. There is no time constraint. But in fact, the student who worked on this is now working at GE. He looks after the cybersecurity activities of GE owned assets like wind farms or aircraft engines, those kind of things. So he looks at the cybersecurity of those kind of systems, and he'll be giving a guest lecture on 25th November. So he's going through the GE approval process. Like if you are in a company, you can't really just come and talk about stuff. You have to take approval from higher ups. So that's going through the approval chain. So hopefully on November 25th, he'll present the kind of work that he's doing at GE in the classroom. So anyways, this is the algorithm we designed. The critical thing here is in the previous dynamic watermarking algorithm, you could only use that algorithm because everything was linear Gaussian, so you can add a Gaussian noise, you can come up with a covariance matrix, and then you can do a lot of stuff with the covariance matrix. The problem with the finite state system was there is no covariance matrix to compute, there is no residual, there is no notion of noise. So we had to come up with a different way of looking at the problem, and we came up with this approach that I've noted down here. The good thing is that once you know what this approach is, now you can do it for any state space and any action space. The only thing you will have to do is just make sure that this hypothesis test is set up correctly. And as long as you have a way to check for this hypothesis, you can come up with the test statistics, and you can write. You will be able to detect the attack at the time it is happening. For instance, remember we had talked about this MMD based change detection algorithm, wherein the null you didn't need to know the pre-change kernel also, and you don't need to know the post-change kernel also. Both of them can be unknown. So if you have a general state Markov chains, general state problem where xt could be some bunch of categorical variables and a bunch of real numbers. So for instance, in the case of this room, you could have temperature, which is a real number. It can be between 0 to 100. But you could also have a vent that is open or closed. So it has only 2 states, open or closed. So now you have 2-state system, wherein one of the state is categorical in nature, another state is actually a real number. So again, that algorithm will not work. The algorithm we talked about, dynamic watermarking algorithm, the one we talked about last Wednesday, that will not work because that requires state space, the entire state space to be a real number. So that will not work. This algorithm I talked about will not work because this requires all the states and actions to be finite values, like you can have 1 to n. So this will also not work, but because the MMD can be defined on arbitrary state space, you can actually detect the attacks on arbitrary state space as well using basically the same approach. But we don't cover it in the class because we have not written a paper on it. Hopefully we'll write a paper on it and then I can teach it in the class 5-6 years later. But for now that algorithm is certainly doable, but we don't have any results around it. Any questions so far on this? Yes.
You have mentioned the attack has to be persistent, right?
Yes.
So if there is an aperiodic or irregular attack,
then it's very difficult to detect it. Actually, those kind of attacks, like most of the attack detection algorithms, assumes that there is a persistent attacker. So now the question is, I think it's an important thing to know. So for instance, if your mean time, mean delay, like when the attack starts and when you detect the attack, if the mean delay is of the order of 5 minutes, then you want the attacker to be persistent for 10 or 15 minutes. Okay. However, if your mean delay is 10 days, then if your attacker is only going to attack for 5 days and then not going to attack for another 10 days, then it's very difficult to detect those kind of attacks. In fact, whenever the data exfiltration attacks happens, when you hear Experian data got lost, somebody stole Experian data, this data, that data, those kind of attacks are actually very low intensity attacks. So very low intensity attacks, and those are periodic attacks. So the mean delay is extremely high because the attack is very low intensity. So you are accessing, you are downloading, when you go through if you look at it from a university's point of view, how many students and faculty are there? Maybe like some 60,000 people are there who access their OSU email every day. So the amount of email that is going out of the servers of Microsoft to our desktop will be of the order of 20 terabytes every day. I don't know, I'm just making up a number. Now if an attacker comes in and he or she is only extracting 2 megabytes, 10 gigabytes of data, it's actually going to remain undetected for a very long period of time. And in addition, if they are periodic, it becomes even more difficult for Microsoft to raise an alarm that okay, somebody is actually actively downloading OSU emails. Okay, so those are some of the things that as a cybersecurity engineer you have to keep it in mind, which is if something is very critical and you need to detect an attack, the strength of the watermark has to be very high so that the mean delay is very small. So that if an attacker is persistently attacking for more time than the mean delay, you will be able to detect the attack with high probability. Okay. Any other question? No? Okay. So this gets us towards the end of the attack detection algorithm. So we have covered a lot of different attack detection algorithms, starting from very simple algorithms that detects if the support of the random variables have changed, all the way until today where we are looking at if the transition probability itself has changed or not. Okay? And we have studied a lot of different algorithms for different settings. So I think what we have done so far, we have covered a lot of different algorithms that can detect an attack, and hopefully what you have also learned so far is how do you set up the problem of attack detection in the case of autonomous system. Now what we will do from the next class onwards is figure out how to mitigate the attack. So now that we have detected that attack is happening, how do we come up with the control action, control strategy, estimation strategy to prevent that attack from creating nuisance within the system. So that will be the subject of study all the way for the this week, next week. So this week we have 2 classes, next week we have 2 classes, the week after that we have 3 classes. So we will be looking into those problems. And then on 25th, my student who worked on this, ex-student who worked on this and now works at GE, he's going to talk about what kind of work he's doing at GE, potentially what opportunities are there at GE. So if any of you want to apply to GE, what would be the way to proceed. So he'll talk about that, and then that will be the last class. okay, for the semester. After that, I'll expect you guys to submit your project report, not project report, your presentation is due on December 2nd, which is Monday. And on December 2nd and on December 4th, during the class time, each of you will get 10 minutes to present your attack detection / mitigation project, and you will be graded on the basis of both your presentation as well as what you've done during the presentation. So we'll do that on December 2nd and 4th. So we have only 8 classes left. No, 7 classes left, and then the 8th class is going to be a presentation. So thank you so much, and we'll see you on Wednesday.